This is geometry. We're going to work on a triangle ratios investigation. So you're going to take your triangle, you're going to take the millimeters on your ruler. What we're first going to do is look at this triangle ABC. ABC is the smaller of the triangles. Take those sides of the smaller of the triangle. We notice from angle A that when you're next to angle A, when you're the leg next to angle A, you're considered the adjacent side. When you're across, when you're not a side that makes the angle A, when you're across from it, you are the opposite side. And then when you're across from the 90, when you're the longest side of this right triangle, you're considered the hypotenuse. So first of all, identifying these sides is really important. We're going to come down to our table. We're using our angle A. We're going to take the side adjacent to the angle A, which is AC, and we're going to look for that measurement. We're going to use millimeters, so looking at your ruler, these are called centimeters. The tick marks in between the centimeters are the millimeters. So we're going to zoom in. And to the best that you can, you need to be as accurate as possible for these numbers to come out well. And we look here and we notice the 1, 2, 3, 4, those are centimeters, so it's really 10, 20, 30, 40, 50, that's about 55, maybe a tad farther than 55. I don't quite think it's all the way to 56. So if we want to call that 55 and a half, or you can call it 55, your choice. So at AC, we'll call that 55. We'll come on down to BC, and we'll measure the length of BC. Again, you've got to take your time to line up the 0 for the millimeters. We got 5, 10, 15, 20. So that looks about 24, not quite 25. So that's 24. That's the BC. Then the hypotenuse. It looks like 10, 20, 30, 40, 50, 60. Just about 60, maybe a half a one further, but not to 61, that's for sure. So if you want to call that 60, you can, or 60.5, whatever you think's most accurate. Now we're going to start to do some ratios. We're going to look at the opposite leg over the hypotenuse. If we come back up to our triangle, we notice the opposite side of our angle A is BC, and the hypotenuse is the AB. So BC over AB. BC we calculated to be 24. AB we calculated to be 60. We could reduce that. And we can also type that into a calculator if I can get it not to be glary on the screen here. So we have 24 divided by 60. And that comes out to be like perfectly 0.4, it looks like. Then we're going to look at the adjacent leg over the hypotenuse. The adjacent side was the AC, and the hypotenuse is the AB. So we're looking at side AC compared to the AB. AC in our calculation was 55. AB was 60. We could reduce that. So we get 55 divided by 60, and that comes out to be 0.916. We could round that to 0.917. Now we're going to look at the opposite leg, which is BC, and the adjacent leg, which is AC. And BC was 24, and AC was 55. (24) divided by 55. That comes up to be 0.4363, so 0.436. So these numbers would be a little bit different if our values were a little bit different. So if you were not super accurate in your calculation, and you weren't taking time to line up your ruler as accurate as possible, your values could start to stray to be a little bit different. Just being as accurate as you can is what we're trying to do. So now we're going to look at triangle ADE. ADE is the larger triangle. A to D to E. So now we're looking at that blue triangle. Of course, the adjacent side abbreviated ADJ. That would be the adjacent side. That's the side next to the angle. The side opposite would be way off on the other side, not touching the A actually. And then the hypotenuse, of course, is abbreviated HYP often, and that would be that side. So you go ahead, measure your triangle sides using the millimeters, fill out your chart, and see how you did. You can pause the video, do your calculations, fill out your table, and come back and see how it compares to what we have. So we did some of our measurements. We got 83, 36, and 90. Yours may be within a half or a millimeter different, but you need to be as accurate as you can for these values to match up. Now we're going to look at the opposite over the hypotenuse. The opposite side is DE. The hypotenuse was AD. We know that by coming back up to our shape. The opposite was DE, and the hypotenuse was AD. So from the angle, the opposite side is across from it, and the hypotenuse is always across from the right angle. So DE, I calculated or measured 36, and AD was 90. It was a question, was it a little bit longer than 90? I chose to use the number 90. Let's see how that comes out here. 36 divided by 90 gives me 0.4. And if you notice, 0.4 matches this one exactly. So they have the same exact ratio. That worked out perfect. The adjacent side, which would be AE. The hypotenuse, which is still AD. AE was 83. AD was 90. (83) divided by 90 is 0.922. 0.92. We see that that's a little bit off of this one up here. But that's the measurements we had. Perhaps the 83 wasn't quite 83. Maybe it was a little bit more. Maybe it was a little bit less. But our calculations here came off a tad, but it's still really close. They're still 0.05 away from each other. And then we have the opposite, which is DE, and the adjacent, which is AE. DE was 36, and AE was 83. (36) and 83. That came up to be 0.433. We would round that to 0.434. And again, we are 0.002 away from having that exact value. So that's not too far apart. So what we're noticing here is that we measured two different triangles. These two different triangles have the same angle. They're both right triangles. The pink triangle and the blue triangle are both right triangles. They both have a 24-degree angle. And when we do the ratios to them, we take the side lengths and compare them. Decimals are easier to compare. We see that they come out to be, if not exactly the same, like we were here, they come out super close, 0.005 away from each other. 0.002 away from each other in this case. The more accurate our calculations, I would expect these to be exactly the same. So go ahead and work with the largest triangle now. We have the adjacent side, which is all the way down, and the hypotenuse is all the way to the top. And the opposite side is across from the 24. So in our future lessons, it's going to be very important for you to understand where is the adjacent side. The adjacent side is not the hypotenuse. The adjacent side is the leg that helps make that angle. That's always your adjacent side. The opposite side is always the one that does not make the angle, always the one across from it. And then, of course, the hypotenuse is the longest side, or the across from the 90. So go ahead, pause the video, do some measurements, come back and check it out. So we came up with some measurements. AG was 111 or 112, so I put down 111.5. FG was between 49 and 50, so I put down 49.5. AF was 122. So if we look at the opposite side, FG, and the hypotenuse, AF, FG was 49.5. AF was 122. In our calculation, 49.5 divided by 122, that came out to be 0.405, so 0.406. So 0.40 is exactly what we had before. And then my decimals kind of went up to 0.06. So that's super close to what we had. The adjacent side was AG. The hypotenuse was AF. AG was 111.5 over 122. 0.913 or 0.914. And then our last set of measurements was FG and AG. 49.5 and 111.5. 49.5 and 111.5. They got 0.444. So what we're trying to recognize is how close these different triangles had the same ratio. What we're going to finish up on your own is the opposite side. What did you see? What were your values? We're not finding the average of the classes at the moment, but what were your values for 4, 5, and 6? Sine, cosine, and tangent are part of your calculator, and you need to be sure you're in degree mode.